This is Unit 7, Video 11. In this short video, we'll follow up the discussion on the previous video about calorimetry, except here we will introduce something called a bomb calorimeter. And this device is an official device that's used to determine the caloric content, how many calories are present in food. And essentially we're going to be undergoing a combustion reaction. That's why it's called a bomb calorimeter. It refers to combustion. Because anytime you eat food, that food is technically combusted by your body to provide heat. So we can actually simulate this in a device. And what happens is this device is a sealed system that has a bunch of water in it. And this water, just like in the previous calorimeter, the coffee cup or the little laboratory calorimeter, the water is the one absorbing the heat, and the temperature change that's going to be measured here with a thermometer will tell us how much heat was released by the reaction. Now, the reaction vessel itself is all the way on the inside, and what they do is they powder the substance to be combusted, usually some sort of food. First, the food is dried, and then after it's dried, it's powdered, so it's easier to react. And then inside this vessel, then this substance, the food item, is placed in here. It's also filled with a bunch of oxygen to make sure we have excess oxygen in the reaction. And then with wires, they will ignite the mixture, and a combustion reaction essentially is going to happen. A sudden explosion will happen inside this chamber. That explosion will release heat to the outside. Here we have a stirrer to make sure that the heat is distributed evenly, and the heat will be registered by a thermometer. And by checking the change in temperature, you'll be able to find out how much heat was inside this reaction. It's really the same thing as before, except more sophisticated, more precise. Now, the equation that we're going to use in bomb calorimetry is slightly modified. So here it says the heat capacity of the calorimeter is now determined not of water but of the calorimeter. And the equation now says heat, Q, is equal to the heat capacity of the calorimeter times delta T. Now notice there is no M here, so the M is missing. So the grams in the calorimeter essentially are set. And that's why the amount of water doesn't change in the calorimeter, so we can actually work that in, or we're not ignoring that, we're just working it in to the heat capacity, and the heat capacity itself actually contains the mass in it. And that's why it's a modified equation. So it's instead of MCAT, it's just CAT. So this is the CAT equation. You'll see that the heat capacity of the calorimeter has the mass unit in it here in a minute. All right, so let's take a look. So, actually, it does not need the mass unit in it. I apologize. It does not have the mass unit. The heat capacity of the calorimeter is right here. So here is the example, 4.812 kilojoules per degree Celsius. So it's actually set. The amount of mass is the same, so we can ignore that. Okay, so we have a sample that's going to be combusted. In this case, we're actually combusting something called lactic acid, which is just the hydrocarbon in chemistry. And we have this much of it, and the temperature goes from 2310 up to 2495. So there's our temperature change. Now we want the heat of the reaction of lactic acid. So again, we're solving for the delta H. And delta H, remember, goes on the back of a chemical equation. In this case, the chemical equation, actually in all cases with a bomb calorimeter, the chemical equation will be a combustion reaction. So what you've got here is you've got lactic acid, which is HC3H5O3. It is reacted with oxygen gas to always give CO2 and H2O. And then the delta H of the system is going to be kilojoules per mole. So what we'll do, as before, we'll find out how many joules, or in this case kilojoules because the heat capacity is given in kilojoules, how many kilojoules is released just by reacting 0.5865, and then we'll scale that up to a mole. So the equation is CAT. In this case, it's just the CAT equation, just like so. And the heat capacity of the calorimeter is given to us as 4.812. Notice it's kilojoules per degree Celsius, not joules, since the calorimeter is a big device. But the change in temperature, it looks like we're going up by not much. Usually it's a small temperature change to make sure we have accurate data. And so we have 1.85. So 1.85 degrees Celsius for that. All right, if you simply multiply those two numbers together, we got 4.812 times 1.85 equals 8.902. This will be kilojoules. You'll notice that degree Celsius cancels out. And I should say, the reason why the heat capacity is such a big number is it allows us to have a small temperature change and still achieve good results. Because if there's a big temperature change, then you'll have an error in your calculation. The heat will be dissipated, and you try to minimize the error by having a small temperature change. All right, so this is just kilojoules. What we need is kilojoules per mole. So we simply need to convert the lactic acid into moles. So what we'll do is we have 0.5865 grams, and then we're going to convert from grams to moles. Now we got lactic acid, so we have 3 carbons, 3 oxygens, and 6 hydrogens. So 3 carbons will give us 3603. 3 oxygens should give us 48, and 6 hydrogens should give us 6.06. Hopefully you got 90.09 grams in a mole. So if I divide 0.5865 by 90.09, I get myself 0.00651. Oh, you get 4 sig figs. This is moles of reactant. Now, the reason why we're doing this again, because we have kilojoules per mole in our unit, and the amount that we reacted was not a mole, it was quite a bit under a mole. So what we were doing here, we're going to scale it up to a mole. So now, we simply divide the kilojoules by the moles. So we got 8.902 kilojoules divided by 0.06510 moles. And this will give us our delta H. So we're solving for delta H here. So let's divide those two numbers and see what we get. 8.902 over 0.06510. Should be a big number. Heats of combustion for big samples like this will be huge. So this is actually 1,367. Now sig fig wise, we're going to actually keep 4 sig figs. Looks like 4 sig figs will do it for us. Actually 3 sig figs because of the temperature change. So actually 1370 kilojoules per mole. So the heat of combustion of lactic acid is actually 1370 kilojoules per mole. And that's how we're going to go about one of these problems. I'll be able to do a few of these, and we'll give you some practice problems in class. Until then.